Welcome to section 3.3, the missing member. Are some infinities larger than others? Remember to take notes, pause the video often, answer the questions, replay this as many times as you need to. So our question of the day, is there an infinite set bigger than the natural numbers? So before we get into something new, let's go back to something old. Dodgeball. This game was played back in chapter 1, and the idea was that player 1 begins by filling in the first horizontal row with a run of X's and O's, and it doesn't matter, they get to pick whatever they want. And then player 2 places either an X or an O in the first box of their board, and these should be there. At this point, so I'm going to put something here, an X or an O. And then at this point, then player 1 has filled in the first row, and player 2 has filled in the first box with their one letter. And I'm going to pick O, and we'll talk about why. And then we so on and so forth. So maybe, they get creative, right? They see we put an O, so they put a bunch of O's. And then I'm just going to put, what am I going to put here? I'm going to look here, and I'm going to put an X. And maybe you remember how to play this game. But the idea is that player 1 wins if any of their rows, and I apologize for these pronouns here, player 1 wins if any of their rows exactly matches player 2's rows, and player 2 wins if their row does not match any of player 1's rows. So basically, the idea is that you could fill all these in, and you want to match whatever the other person did here, right? So this person is trying to match. So they're trying to guess. And so would you rather be player 1 or player 2? And what we learned was that we want to be player 2. And the strategy that guarantees victory is that as we go through, we're going to look, okay, at their first row, they put an X, we're going to put an O. And then we go through, and then they think they're getting clever. But then at the second line, we're going to put the opposite. And then they try to match us. And at their third line, we just do the opposite. And no matter what they try to do, at the fourth line, we just do the opposite. And so we're always doing what they don't have. At the fifth line, we do the opposite so that they can't match us. Maybe they do another O. So they can't match us. And so we're going to continue that as we go forward. In looking at these infinity questions. So before we go forward, again, just remember that the natural numbers represented here with that N, Z, integers, and Q rational numbers, they all have the same cardinality, and we proved that back in 3.2. So to find a set of greater cardinality, right, we know that these are the same, we need to find a set whose elements cannot be listed. Because every time we listed the elements, we were able to create that one-to-one correspondence. So what we need for a greater cardinality is where I cannot list all the elements to match them with my natural numbers. So Cantor said, and this is the theorem, there are more real numbers than natural numbers. So to show that the real numbers are more numerous than the natural numbers, Cantor focused intently on what it would mean first if they had the same cardinality, back what we showed in the last section. So it would mean that the real and natural numbers could be put in one-to-one correspondence. That would be the same cardinality. So writing down that such a correspondence might look like gives us a visual clue as to why any attempted correspondence between the natural numbers and the real numbers could not include every real number. Some real numbers must be missing. So basically what that's saying is, okay, I'm going to try to match it. But what I'm saying is that there are some real numbers that I can't list. Some real will always be missing if it's bigger. If it's not bigger, then I can list them all. But the idea is that there's some secret R that isn't getting shown there. So first, let's go back and remember how we express decimals. We can express decimals with infinitely long decimal expansions, and then it's a real number. And we should take a moment here just to recall our real numbers. They include our integers, they include our natural numbers, they include our rational numbers, and then they include our irrational numbers and our infinitely long decimal expansions. So now let's talk about comparing decimals. What do you know about these two numbers? Okay, Well, I know that I only know this fifth digit here, right? There's the decimal point. I only know this fifth digit. And I guess I know that these two numbers are different because they have a different fifth digit. So if we have two numbers, one with a 2 and one with a 4, and let's say the 87th digit place, and I'm certainly not going to write out 87, but in that 87th, let's say 87th place, if one has a 2 and the other one has a 4, we can say that they must be different numbers, because to be the same, they would need the same decimal expansion. So Cantor's method to prove that there are more real numbers than natural numbers was basically to say that there is I can construct some real number that will not appear in the list. That's all. If we list our natural numbers in the left, 1, 2, 3, 4, and I list reals in the right, there's going to be some real that's hiding out and not on the list. And so that is what we are going to set out to try and do here. He showed that once we commit ourselves to a list of real numbers in the right-hand column, there will be one real number corresponding to the natural numbers. And so all the natural numbers will be taken. So then we're going to find a real decimal number that does not appear anywhere on that list. So we could not have listed all the real numbers because I've got one that isn't listed. But the natural numbers are already going to be taken up. Those will already be corresponding to all those reals listed. So there's at least one real that isn't on the list. Therefore, there must be more real numbers than natural numbers. And pause it here, maybe play that a few times. It's quite confusing. So again, we could not have listed all the real numbers in the right-hand column. That's the idea here. Once we say that these are the reals in the right-hand column, the natural numbers are taken up, and there's some real number that if we can write it, it's not on the list and it doesn't match with the natural number. So there are more real numbers than natural numbers. Now let's think about it in terms of barrels. Imagine that we have the natural number barrel and a real number barrel. And we're just going to reach in and grab numbers one at a time and pair them up. So maybe we grab 1 and we pair it up with 2.73249. And then maybe we grab 2, and that real number is negative square root of 3. And then we grab 3, and we go on. And that's the idea. We're just going to keep grabbing numbers out of that barrel, and they could be any number. And we're going to make a list of them, and we're just going to use this list here. So this list here says I pulled a 1 out of the natural barrel, and this was the real that came out of it. I pulled a natural number, and this was the real, and so on and so forth forever. And I'm going to keep doing that because both of those barrels are infinite. So now let's consider, will every single real number appear somewhere in that right-hand list? Okay, well, Cantor says no. Cantor says that there is going to be some real number over here that is not listed, that's going to be left in the barrel after all the natural numbers are pulled. So let's try to construct that number. And we're going to use an idea similar to Dodgeball. And what we are going to do is the following. We're going to write down a particular number. We're going to call it M for missing. And we're going to say it's between 0 and 1. And so it's going to have a decimal expansion of 0 point, and then we don't know, right? But we're going to make some rules. And we're going to decide those digits, what they are. And we're just going to say, hey, it's either going to be a 2 or a 4. We could have said 1 or 3. We could have said anything, but we're just going to say 2 or 4. And we're going to decide these in the following way. And remember, think back to Dodgeball as we do this. We're going to compare the first real number that could be pulled from the barrel and listed and compared with the natural number 1. So the idea here is that real number that got pulled out of the barrel to go with 1, it either has a 2 after the decimal point or it doesn't, right? So we're looking at this point here. Either that number has a 2, so it looks like this, or it doesn't have a 2, right? And if it has a 2, we're going to make our number have a 4. And if it does not have a 2, then we're going to make our number have a 2. And then the second digit after, and this should be second digit after, we are going to see if it's going to be a 2 or a 4. So now we're looking at the second digit in that real number that matches with the 2. Is it a 2 or a 4? And this is actually easier to explain as I show it. And we go on and on forever through the 11th digit. And we're going to actually do this now. So I'm just going to make this a little bit smaller here. So let's say we know that M, we're going to construct a number that is missing from the table. And you know what? We're going to do it starting with 0. Point. Now, we're going to look at the one that matches with 1 and the first digit. Is it a 2 or not a 2? It is not a 2, so our number is going to be a 2. Now let's look at 2. So the second digit after is a 2, so our number is going to be a 4. Let's look at the third digit, 1, 2, 3. It's a 2, so we're going to make ours a 4. Let's look at the fourth digit, 1, 2, 3, 4. It's a 2, so we're going to make ours a 4. 5, 1, 2, 3, 4, 5. It's not a 2, so we're going to make ours a 2. 6, 1, 2, 3, 4, 5, 6. It's a 2, so we're going to make ours a 4. And we can do this forever. And just like in Dodgeball, we can guarantee that we're going to win. We can guarantee that this number will never be on here, and therefore it does have a greater cardinality. So let's just double check here. How do we know if M is really missing? Could M appear anywhere on this list? And if so, where could it appear? And, okay, could it appear with 1? Well, let's look at 1. No, I know that the 1 has a second digit of a 2, so it definitely can't correspond to 1. How about 2? Well, I know that the second digit there is a 2 and ours is a 4, so I know it can't correspond with that. What about the number that corresponds to, and actually it should be this way because these are their naturals. Could this be M? No. And then what about the number 1,582,987? Will that correspond to M? And I'll tell you what, it will not, because I'll make sure that the 1,582,987th digit does not match. And so the answer is that it cannot be on there. And so when we look here, it was called the diagonalization proof. And can you see why? Oops, let's get it here. Can you see why? You go across diagonally. So maybe you think like, hey, this guy must have been considered a genius, but the answer is that he actually wasn't, and people were not okay with this idea. And it kind of goes back to 1637 with Galileo. Remember, he was imprisoned for saying that the earth moves around the sun. The mathematical community really struggled with this idea that the real numbers were greater than the natural numbers. So don't feel bad if you're struggling to get a handle on it, because it's hard to make sense of it. And think about other aspects of your life where the counterintuitive and considering the counterintuitive might apply. So we've shown that if we are given any correspondence between the natural numbers and the real numbers, we can produce that missing number that doesn't correspond. Therefore, we have different sizes of infinity. The cardinality of the natural numbers is not the same as the cardinality of the real numbers, even though they're both infinite. So there are more real numbers than there are natural numbers. And that concludes section 3.3.